Hello everyone, I'm Shao Yucai, PhD student from School of Creative Media, City University of Hong Kong. I will present our recent work, ThermAirGlove, a pneumatic glove for thermal perception and material identification in virtual reality. Well, ThermAirGlove, it can provide controlled thermal feedback to support material identification in virtual environments and improve immersive experience in VR. And this work was done by City University of Hong Kong and the University of Tokyo. Look at this figure. A user is wearing thermal air glove when he's grasping the copper ball in VR, and this is a VR sense, and this is the contacting temperature change, which is similar with the real physical object made with copper material. In our daily life, when a real object is grasped in the hand, its surface material can be informed by the thermal cues. For different materials such as plastic, foam, steel, and glass, we can perceive different levels of thermal sensations when we touch them one by one. Well, for example, when we touch a metallic bottle surface, we may feel cooler than a plastic bottle. The wooden door feels warmer than the metallic door handle, and this is because the thermal conductivity and heat capacity are different among these materials. So, it is possible to infer objects' material based on the temperature change of human skin when contacting any object surface. Well, in host research, it gave us a long process of thermal interaction supporting material identification. When humans contact or touch the real physical objects, and the skin temperature response comes from the thermal receptors inside the skin to support cognitive process of material discrimination and recognition. Well, for different materials with significantly different thermal properties such as foam, glass, and aluminum, the total change in skin temperature are different. It has been proved in the real physical objects, but it is challenging to perceive the virtual objects materials in VR. Well, generally, the rigid material elements can provide controlled thermal cues or thermal feedback for users, and some previous research have proved that it is feasible to achieve material simulation by thermal controlling through material elements. But actually, directly attaching the rigid material elements on the user's hand may cause movement restriction, which can affect the user's experience in VR. Well, on the other hand, the pneumatic wearable device is feasible and lightness. It is possible to use a pneumatic device to provide thermal feedback instead of material elements to support material identification in VR. So to explore the feasibility of material identification in VR, in our work, we present ThermAirGlove, which is a pneumatic glove with embedded airbags inside the nylon elastic glove to generate controllable pneumatic thermal feedback. And this is an RGB image of ThermAirGlove, and this is the thermal image of ThermAirGlove. So look at this picture, you can see the ThermAirGlove could quickly change its temperature when pumping cold air into the airbags. Well, we designed the ThermAirGlove consisting of a pneumatic glove with 5 inflatable airbags attaching on fingers and the palm, and 2 temperature chambers, 1 hot and 1 cold, and a pneumatic and temperature air pumping system. The airbags are made with the thin and light PE sheets, and there is a Type K thermocouple installed in the middle finger airbag. Well, the thermocouple will sense the user's skin temperature and provides real-time recording temperature for air pumping system. And we also developed these 2 temperature chambers using criteria-based modules, and there were 2 criterias inside the chamber with the heatsink toolkits outside. For the hot chamber, the maximum temperature is at 68 degrees, and for the cold chamber is about 2 degrees. An external 24 voltage and 5 ampere power supplies to drive the pneumatic system, and this is a wall design of hardware for our system. And this is a system diagram of ThermAirGlove. In the thermal and pneumatic control system, we use an Arduino board. chose 3 air pumps for inflation and 1 pump for deflation through servo valves. And to reduce the heat transfer during the pumping process, the cold and hot pumps were placed into the temperature chambers. Well, we use HTC Vive Pro headset and lip motion to detect hand gestures. When user wearing thermal air glove, the pump tube will deflate the airbags. When touching or grasping different materials in virtual environments, and the thermocouple will return the real-time temperature, and the system will control pump 1, pump 3, and pump 4 to mix hot, cold, and room temperature air to maintain the target temperature in the airbags. And this is an example for thermal air glove application. A user is wearing thermal air glove and touch a wooden box with a copper lid. So you can see when touching these 2 different parts, the temperature sensor is showing different changing levels for these 2 different parts. And we firstly technically evaluated temperature tracking performance for thermal air glove. Firstly, we measure different thermal parameters. And we assume the skin temperature is 13.4 degrees, which is neutral for most people. And then we set 2 directions of change, warming and cooling, 2 rates of change, 1 degree per second and 2 degrees per second, and 3 intensities of change, 2, 4, and 6 degrees. So we totally test 2, multiple 3, 12 different kinds of combination for thermal parameters, which is shown in this table. And then we measure the step response of temperature change for different 12 thermal stimuli, and we also include 34 degree as a neutral stimuli. So we totally, so there were totally 13 stimuli. We also calculated the MAE, mean absolute error, and MME for this 13 stimuli, and the average MAE for propagational stage is 0.137 degree, and the MAE for stable change is 0.31 degree. So you can see the temperature signals could follow the theoretical trends. And then we adopt a simple infinity body model for our system to evaluate human skin contact process for thermal-based material simulation. And the semi-infinity body model has been widely used in material simulation in the real-world objects. So we want to take this model as a reference for our system. And these formulas show the change of human skin temperature. TST is the skin temperature change after contacting, and TSI and TOI are the initial skin temperature, initial temperature of skin and materials. K, rho, and C are some constants, which are thermal conductivity, density, and the heat values. RSO can be calculated with these constants, which is thermal contact resistance. And then we adapted the thermal infinity body model on 3 kinds of different materials, copper, glass, and foam. We tried to fit the temperature of airbag surface with a theoretical model for the 3 different materials. And this is a result of simulated copper. When the user is grasping the virtual spheres, the initial skin temperature is about 13.4 degrees. With the PID control, the thermal air glove system could reach the thermal equilibrium within 2 seconds from 13.4 degree to 28 degree and maintain the temperature from 26 to 27 degree in the following time. And for the temperature, for the result of simulated glass, you can see the average temperature change speed is about 1.78 degree per second within the first 2 seconds. And this is a result of simulated foam. You can see we could find there was no significant change for the contacting temperature. Well, this is a comparison results between the reference simulated results, which is a dotted line, and the system simulated results, which is a solid line. From the figure, we can see the ThermAirGlove system simulated results could reach the similar changing trends and the final temperature with the theoretical simulated results. And in addition, in order to quantitatively evaluate our system, we also calculated MAE for every material in the temperature changing stage, which is within 2 seconds after contacting, and the following stable stage. For more details, you can find our paper. Well, based on the temperature tracking performance evaluation, we conducted the first user perception experiment to measure participants' subjective thermal intensity. And this is the setup of our experiment. Participants were required to give the perceived thermal intensity by moving the slider in a continuous scale from cold to hot. We collected the scores for 13 different thermal stimuli in temperature tracking experiment, and more details about experiments procedure could be found in our paper. The results show that the cooling sensation is more intensive than warming sensation, and there is a significant difference in intensity of change between 2 degree and 6 degree and 2 degree and 4 degree, and the fast rate of change is significantly more intensive than the lower rate. And in addition, we performed K-means clustering processing to classify 30 stimuli. The results showed our system could generate 5 distinguishable levels of stimuli from very cold to very warm. And post-hoc pairwise shows significant difference of thermal intensity rating between our clusters. And then we conducted another user perception experiment for materials identification among copper, glass, and foam. And the setup for this experiment was similar with the previous user perception experiment. Well, in this experiment, 2 types of material simulation, the real objects and the temperature signals of ThermAirGlove were presented to the participants in 2 sequential sessions in a counterbalanced order. The results showed our ThermAirGlove system could achieve the average accuracy of 87.2%, which could support users' material identification with no significant difference compared to perceived real physical objects. And finally, we conducted user studies on their experience with ThermAirGlove. We compared 3 conditions of objects manipulation using bare hands without ThermAirGlove, denoted as bare hand, wearing ThermAirGlove with room temperature air but without any temperature and material simulation, denoted as ThermAirGlove F, and wearing ThermAirGlove with thermal feedback and material simulation, denoted as ThermAirGlove TF. Well, the results showed using ThermAirGlove in immersive VR could significantly improve users' experience of prisons compared to current commercial VR settings and ThermAirGlove system without any temperature or material simulation, ThermAirGlove F. Lastly, in conclusion, we present ThermAirGlove, a pneumatic glove with embedded airbags, which provides on-hand control thermal feedback for users. A series of user perception experiments shows the ThermAirGlove system could provide 5 distinguishable levels of thermal sensation and thermal feedback to support users' material identification, which can improve immersive experience in VR. However, we also identified a few limitations in our current system. Firstly, in thermal intensity rating parts, the system didn't cover all the range of thermal intensity rating, which means the participants didn't perceive extremely hot and cold sensations. This could be due to the heat transfer between the air in the tube and the environment during the air pumping process. This could be solved with better isolation in the future. And in addition, mainly test 3 kinds of materials: copper, glass, and foam. This is because we follow the real material discrimination experiment, as they have largely different from each other in terms of thermal properties. Well, in the future, we want to test more kinds of materials for discrimination in virtual environments. And lastly, our system mainly focuses on controlling the pneumatic thermal signals, but there's no closed-loop control mechanism for the air pressure feedback. Actually, it is challenging to combine concurrent controlled force and thermal feedback in a single system. So in the future, we want to explore how to generate controlled force feedback based on current ThermAirGlove system. Okay, that's my presentation. Thank you for the listening. Feel free to give some comments.